2017.
Hi, everyone. So I'm Vitor Ventura. Well, first of all, we have some disclaimer. It's our own view, so does not necessarily represent IBM position on this. So I'm Vitor Ventura. I work for IBM X-Force Red. Well, blah 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 blah. I don't really think that this really matters what I am or what I have. So, Vladan.
Yep, thank you. So, a little bit about me. I work for the same team as Vitor. It is IBM X-Force Red team. We cover EMEA region, and we have a lot of work in different areas of security, covering embedded devices, reverse engineering, and penetration testing. So, why are we going to speak today about this topic? Very recently, we had an interesting project testing one device which might be used in automotive industry, and it was based on FreeRTOS and ARM cores. And we had some interesting findings during this project. And also, we discovered that there are not too much resources about security on the FreeRTOS. So that was the big problem on the one side, and the other side, we had some issues actually reversing the embedded firmware for the device when we get to it. So after a lot of time spent reading documentation, reading header files, we decided it might be interesting for some of you which might come into this similar position to share with you some of our findings. So how many of you did some embedded development? Oh, we have some hands, excellent. So that's good. So for you, this couple of slides will not be interesting. So I'm going to show you how a different mindset is needed when you are working on embedded device. We are all used to desktop stuff. We have developing software, we have reversing it, we have analyzing it, and that is something that is common. We know that there we have mostly two architectures, both based on Intel. Most common stuff are running on Windows, so we are very aware of all constraints, and there is a lot of resources about that. Also, hardware is very much hidden from us. There are some drivers which might or might not be interesting to us, but usually hardware is already predefined and we access it as a black box. Operating system provides a black box, so level of abstraction of the hardware to the software world. So that is the main purpose of all drivers in the operating system. And that is very much different in embedded world. In embedded world, we have small CPU, micro CPU usually. There are a lot of choices today. When I started, there was only one or two choices, Intel or Motorola. Now we have a lot of different architectures. And very common and very powerful devices coming for ARM, usually Cortex M0, M3 and M4 devices, because they are of the family which is made for embedded devices. So you have A family of ARM, which is for application purposes, and M, which is for embedded devices. And they came with a lot of peripherals already integrated in it. And problem is, when you're developing for embedded stuff, you need to be aware of both hardware and software. So you cannot just sit and develop software for device that you never saw before, because it will not work. And ubiquity of embedded device is because today we see that embedded devices are everywhere. Today it is much cheaper to put a microcontroller on something than simple transistor before. So you have it everywhere, from the cups for a coffee, which already have some indicators about temperature and stuff, until the small toys, to big toys, to cars. So even our car is one big embedded system with wheels on it, and it's driving, and it's becoming very interesting target for different attacks. So tools of choice are more or less similar from both sides. So we used to work usually with the IDA or radar or whatever on the desktop, and we can use the same on the mobile as long as it supports our target architecture. But problem is, for example, our favorite tool is IDAPRO, of course, but it has some quirks. For example, to load this example firmware that we are going to show you later, we needed to set numerous places to have it decode correctly. So it is a little bit complicated setup. And it is very useful, something that we are not going to show you today because this is still work in progress, is to use structures dynamically created in memory. So this is why we are going to speak a little bit about architecture of FreeRTOS to help us discover functions. So when we are talking about FreeRTOS, it will be a little bit cleaner. So we saw problems with, if any of this is not properly set up, we will have problem with mode and instructions. So if you don't set up this segment default register value to T to 1, it will not decode thumb instructions properly, for example. Or you will have to manually switch each line to thumb mode. As any embedded devices, we always say they are everywhere. Most popular embedded devices are currently running on Mars. So imagine designing something and to put it millions of kilometers away and to try to fix it, debug it, and maintain it. It is a big problem, and developers need to be aware of that they have a limited amount of memory and resources. They must be aware that power consumption must be controlled. They must take care of real-time responses, and the device must be self-sustainable and resilient. What does it mean? About 200 days after the Mars rover landed on Mars, there was an issue. It has two computers in it for resilience, and they are designed in case the primary computer has any problems to shut down and hand over to the secondary computer. Problem was the device stopped responding to any commands. Why? Because primary computer was stuck and the device was unable to switch to secondary computer. Luckily, there was a third communication device which was independent of all this, and it was enabled that control from the Earth send commands to shut down primary computer and switch over to secondary computer. So it is very, very important about resilience and self-sustainability of these devices. What are we seeing is that first problems are coming from the hardware side. So you have JTAG and UART ports available. So you are able to connect and debug device. Of course, in case of Mars rover, if somebody sit and start debugging your device, we will have much serious issues than security of that device at this point. But for the Earth-bound device, this is a big issue. We have exposed buses. So you are able to just tap into the wires on device and to read all protocols that are running there if you can decode it, of course. Then we have unprotected storage. For example, you will have device which have internal flash RAM, but it will have also external memory for whatever purpose, for logs, for firmware, for temporary storage, like SD card. So you can tap into that and collect information. There are also a lot of communication interfaces, mostly radio interfaces, which are used for everything, and we already know they are easy to hack from time to time. There are very common debugging consoles are left running. So developers forget to disable debugging features before they release. So that enables us to get to the bootloader. It enables us to download the firmware for devices and to do whatever we need to do with it. So there are also software requirements. And first software requirements, it needs to be tailored specifically to embedded hardware, to hardware of the device, the architecture that we chose. And that's the big problem. You usually have two teams. One is hardware development team, the other is software development team. So hardware team will choose architecture that they think it will work for them. Software team needs to adjust. And that comes to some problem because CPU speed, memory constraint, available storage, they will all impact software development. Of course, again, power consumption, error handling, and bugs resilience. So software developers must be able to adjust their processes and their code to specific architecture. How to do it? There is a lot of different hardware, as we already mentioned. You have different architectures with different NDNS, different peripherals, and you need to account for all possibilities of a combination of different devices. So the common solution for this, use something of existing frameworks and real-time operating systems. which will help you to solve this into controllable manner. One of the very common operating system that I use is FreeRTOS. It is nice because it is open source. It is available on the market for a long time. There is a commercial version which is certified for security, blah, blah, blah. So it might be interesting if you want to take a look at more details on the site that is down there. It runs on almost every possible platform, including Arduino. So if you want to try it at home, you can play with it, no problem. It's easy to port to new platforms. You need to change only 3 files which are hardware dependent. Everything else will run as is. And it supports multitasking, and it has a tiny footprint. So on top of this basic operating system, we have additional modules which are available to make our FreeRTOS device more usable. So first and most important is TCP/IP stack. Then we have FAT file system, command line, and I/O support, which includes GPIO. You all know what is GPIO? Okay, I assume yes. So basic structure of FreeRTOS is as shown here. We have hardware on the lowest level. Then we have hardware-dependent code, those 3 files that I showed you. Then we have core. Those are hardware-independent files, which are same and provide the same functionalities. And we have user code, which will actually be executing on top of FreeRTOS, and it will serve the purpose we intended. So main component is task scheduler. Task scheduler is the orchestrator which will take care of executing tasks. Tasks are programmer-provided pieces of code. So actually it would be like programs on the desktop that runs specific functions and they execute concurrently. So it is multitasking. Each task has a separate stack. And you will see later how that stack is handled. There are core routines. I mentioned this, but this is almost not used anymore. I think it is not even supported anymore. And we have communication, inter-process communications, so data queues to exchange information between processes, semaphore and mutexes for signalization, and timers for measuring time. As we say, real time is really important in this case. The most important structure are lists. Everything in FreeRTOS is contained in some form of lists. So we have a PX task ready list, which is most important list, which has pointers to records of task control blocks. Task control blocks contain all necessary information for the customly created task. So when you create first task, you will create task control block somewhere in memory, and you will add it as a number 1 in your task ready list. But when you create first task, one more task will be automatically created. Which one? Any ideas? Idle, yes. So first task, 0 task will be idle task, which will take care of all the unused CPU cycles, and then all the others. So when you instantiate your first task, it will create automatically idle task. So we have a little bit about queues. So again, there are lists with some specifics to it. Semaphores, they can be binary semaphores or multiple semaphores, and they can be used to communicate between, to signal between the processes. And mutexes are used to protect access to resources during the multitasking. Now, what will happen? If you have 2 tasks, one is of highest priority than the other, and each of them needs to access 2 resources. So first will be started with high-level task. It will create high-level mutex protecting the resource. Then you will have lower task executes. It will create mutex to access the other resource which is not claimed yet by the higher-level task, and it will create mutex. Now you will go into a situation that you're blocked because your high-level task cannot access resource which is blocked by the lower level task, and vice versa. So both tasks are blocked, and you cannot proceed. So FreeRTOS solves this by temporarily raising the level of the process which is waiting for mutex from higher level process. So in this case, lower level task will be upgraded to high level priority. So it will be able to take the mutex and proceed accordingly. It will not be waiting for the higher level task. So there are some security features which are already embedded in FreeRTOS. Some are add-on. So first add-on is SSL library. It doesn't came with FreeRTOS. It is separate library from Wolf SSL, I believe. It is additional. It is much smaller than standard OpenSSL. And if you are aware, most of the vulnerabilities we had in the last couple of years, to serious vulnerabilities, were related to OpenSSL. It became too big for its purpose, and it's difficult to maintain. So this operating system is using another library which is very nice and small and support everything that you actually need. It has some rudimentary stack overflow protection, and it supports different privilege levels for the tasks. But that is limited only to Cortex M3 devices, which have memory protection unit. So in this case, you can create tasks of different privileges. That is not the best approach because it is easy to go around. Problem is that from unprivileged task, you can create privileged task. So if you manage to exploit something that runs under unprivileged task, you can rope your way out of it by creating privileged task and getting access. Difference between privileged and unprivileged tasks are privileged task has access to its own stack and to all other stacks. Unprivileged task can access only his own resources, only his own stack. So we have a stack for overflow protection is rudimentary, so it is in two. There are two possible modes. One will just simple check if your stack pointer is somewhere where in the range where it should be expected. The other one will add small canaries to measure if it is on the expected point. And problem is the TCP/IP stack is not very resilient because this is embedded device. It is not made to suffer harassment of million users connecting to it all the time. So if you do any more intensive, for example, port scan on this device, they might experience some issues. And we see that very often with SCADA devices. So this is why we never scan SCADA devices in the production. They have really sensitive TCP/IP stack. And of course, its FreeRTOS is developed in C. It inherits all the possible issues that you have in any other C programs. To be fair, I was searching for such vulnerabilities in FreeRTOS for 2 months and I couldn't find any. It doesn't mean that they don't exist, but I couldn't find them. But you might find in the custom created tasks, so they can introduce vulnerabilities. FreeRTOS is relatively safe from it, and you can always investigate it because it is open source. And everything that we discussed so far could be found and checked into source codes that are provided on the site. We are going to develop a simple application that Vitor will later be destroying here for purpose of demonstration. And we are going to develop a simple application because it will be easier for us to see and to show you what is important. So we'll create an application which have only 2 goals. One is to check if button is pressed, and if button is pressed, it will toggle the LED. So it is very simple. And this is the basic architecture that first come to mind. So we have core RTOS, we have a task scheduler running the 2 tasks. First task, we check if the button is pressed, do the debounce and everything, and then we'll put in data queue information that button is pressed. The other task is LED toggle task. It will verify if data queue has information that he expects, and he will turn off or turn on the LED accordingly. This is nice, but it is bad. This is not how it is done actually on embedded devices, so I created a little bit better architecture. Problem with first architecture is the device will never go to sleep, so we have problem with power consumption. In this case, I have changed a button handler to be interrupt. So device can go to sleep, and only when you press the button, you will generate interrupt and wake up device. Device will detect that it is waken up by external interrupt, and it will trigger the binary semaphore. It will become available. LED toggle task will wait for binary semaphore to become available, and when he detects that it is available, it will turn on the LED and make semaphore again unavailable. So it cannot do two things. It cannot toggle twice on the same time. So next time, only button handler needs to set the semaphore again. So how it is done? It is very simple. So bolded lines are hardware-dependent lines. So setup hardware is hardware-dependent as expected. Everything else is not hardware-dependent. So we created one task, which is LED semaphore handler task, and we started task scheduler. If we ever get return 1, there is a problem with our application. It should never return. Task scheduler, when it starts running, should never return. And 2 functions. First one is related to LED, so how to toggle the LED. It will check if semaphore is available. It will wait forever. If it is not available, when it becomes available, it will toggle the LED. I give alternate way of triggering LED because it might be interesting for something that Vitor will be showing you later. And we have interrupt handler. In this case, our button is on line 8, so we need specific interrupt which will handle line 8. We check if it is line 8 and do what we need. So we make semaphore available and let LED trigger. What remains is to go from the source to the hardware. So we will do compilation, blah, 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 and we will upload everything to our device, power it on, and we'll detect that it is running. So we have created our first embedded device. We expect some profit from it, of course. We don't do stuff for free. But we make a lot of mistakes, and the Dark Lord of Mordor is looking at you, and he will do something bad to our device. So, Vitor, Dark Lord, please.
Okay, so one of the things that it's interesting, so we have the good thing and the bad thing about these embedded systems. And, well, the good thing is that they are deeply tied into the MCU. And this means that you have a lot of documentation. You can go to the ST Electronics, for instance. For this example, we focused more on the STM32F0 MCU, which is based on the ARM6 M0 core. And the good thing is that the embedded devices, they need to be developed for the specific MCU. So this allows you you will have a lot of documentation about the MCU, the interrupts, all the architecture, and this is a good thing. On the other side, the bad thing is that it's tied to the MCU. So if you have your firmware and you don't know what is the target of it, so it will be hard for you to understand what's going on inside it, because you won't know how the starting addresses, you won't know how to approach it. So it's a good thing and it's a bad thing. So let's imagine that we don't have a lot of string analysis. Usually these kind of systems don't really need to output a lot of things to the user. So if you look at the strings, you don't get that many things, that much information. As Vladan said, because the code the user code on FreeRTOS is embedded so deeply into the operating system, you don't really have the syscalls that you can search for. There are some of them that is reused when you compile your code, like the scheduler, but in reality, you don't have that syscalls to read memory, to read some kind of interrupt. You don't have that, so it's not that easy to look and see where you are going to start. And from the memory point of view, it's not protected. So when your application is running, basically you are reading and writing from all memory addresses, depending on if you are trying to read from a register which is tied to a pin output or input, or if you are looking at on an external interrupt. So everything are memory addresses, so you don't really have the abstraction layer that you have on normal operating systems. And this leads us to some kind of difficulties when you are trying to reverse engineer an application, FreeRTOS image, because you don't really have the usual desktop approach. So the first thing is that we need, by default, when we put the image into either, like Vladan said, you need to set the initial address for the image. You need to have some information, the size of the image. You need to know exactly where to put it, and either will disassemble it. But the thing is the entry point. And it might be not that easy to find the entry point to see how your program is starting. You can wandering around and try to search for it, but it's not that easy. And either you might not detect it. So can we find it? How can we do it? Yes, we can. And one of the things that the ST32, by default, they have a group of interrupt handlers that will by default help the firmware to know how to behave when the MCU boots up. So in order to know where that handlers are, this MCU has the interrupt vector table, which pretty much is a table that holds all the information about what kind of interrupts can exist on the MCU. And one of these interrupts is the reset. So what's the reset more than simply a boot? So when you boot the device, it's a reset. It's nothing else than that. So if we look at this table and we looked for the interrupt, for the reset interrupt handler, we pretty much might have that answer. So if you look there, you see that going from bottom to up, you have, this is the actual table that you can get from the documentation, and you can see that you have the initial stack pointer, and then you have the reset. So this table pretty much goes to this at the beginning of the image, at offset 00. So you can see that you have some code there that is not actually put into that table form. So what we did was we tried to get a plugin that would help us to have a mapping between these values and the actual values that are on the documentation. So these are the two first values that we have, and after we run the script, we'll see it like this. And we also added some comments that will help us to initially understand what's going on. So first we have the stack value, then we have the reset handler, and there are other handlers like theirs, like the SysTick handler or the SVC handler, which are used by the FreeRTOS to manage the tasks. So if we now, after we have this, the both addresses for the interrupt handler, we can go there and we can actually see what is going on. So as soon as this device boots, in this case, what it's doing is basically putting the initial stack address into the stack pointer, which pretty much can be the first action that it does. So now we have an entry point, and this helps us to start our analysis. Now we really can see where our code starts to being executed. Of course, as we said, this is highly dependent on the MCU. So the good thing is that it's well documented, and probably if you know which MCU your image targets, you can go online and search for the documentation, and you will find the description of that table, which will help you to understand exactly what it's doing. So now we have an entry point. We know how to start. But as I said also, everything in RTOS is pretty much reading from memory and writing to memory addresses. So there's no syscalls. So if you remember, I said that all the peripherals inside the MCUs, they are managed by these addresses. So these ranges and these offsets, can they be useful for us? Yeah, of course they can. For that, from reading that, we can understand exactly what our image is doing. So again, we can go to the documentation of the specific MCU, and what we did was, well, since we were doing a plugin to help us, we basically run a plugin that has some information about the documentation, and it will list all the registers that are manipulated, the functions that manipulate each register, so that we can go directly to the code that we want to see. And also it will have comments that will help us to manage it. So in the end, we can see things like this. So for instance, in this case, we know that we are attributing the clock control register. This is important, for instance, because if you want to see a peripheral that has some kind of GPIO read or write, it will have to have a clock control register attributed to it. So if by chance, because some of these addresses can be generated in runtime, even though if you cannot find the specific register where the GPIO is being written, you can search for this kind of registers, which will tell you exactly which GPIO buses are being used. So, because some of these addresses, they can be hard-coded and they can be generated in memory. However, the compiler tends to generate some of them to keep some of them hard-coded so that it doesn't need to make so many operations during execution. The other one that is really interesting to see is the sysdig. The sysdig will generate a clock, basically, and will call the sysdig interrupt every time the clock reaches 0. So if you want to check for tasks that are in a loop, this is the place to go. And this will tell you exactly how the clock is behaving, which is also really important so that if for instance, you have a firmware which is checking on a certain interval for some signal that is coming from an external service, that can be it. So it's also very interesting to check. The other thing is that what we did was, okay, now we can see exactly, as I told, now we can see exactly which functions are manipulating our registers, so we can have a more direct approach. We can look into those functions and see exactly what they are doing. The code of those functions is ARM, so everyone that knows ARM will be able to understand it. So this is much more about what would be the methodology to get there, instead of just looking at the code without really knowing where to look. So in this case, for instance, what we have done is we are looking at the sysdig function, and as we can see up there, we are setting the reload value and we are doing the control register. So these specific registers, they belong to the core, to the ARM core, not to the MCU, because you have two different kinds of registers. You will have the registers which belong to the core, to the ARM core, and you will have the registers which are on the MCU. So they are not the same, and they are protected in different ways. But in this case, this is just an example. What we are seeing here is that we are telling we are configuring the register for the sysdig. So the first one, we are giving it 1,000 ticks, and after 1,000 ticks, it will do something. And that's defined by the second register, so the sysdig control register. So if we look at the documentation, we should be going through the next slide. Oh, sorry, my PowerPoint crashed. Okay, yeah, so we're here. If you look at the documentation, in this case in ARM, you'll see that those 3 bits are the ones that configure actually the register. So when we move the 7 into that register, what we are saying is that, well, we want the clock source to be 1, we want the tick int to be 1, and we want the clock enabled. So the clock source is just saying that it's a hardware clock, it will go directly from the CPU. The tick int is saying that when the clock comes to 0, it will release an interrupt and it will stay, and it will wait. It will not move on to the next cycle, and basically it's enabling the clock. So in this case, what this application is doing is that at every 1,000 clicks, it will generate an interrupt and it will wait. So this is the kind of thing that you will find on the documentation of all MCUs. In this case, all MCUs based on the ARM 6M0 will have this kind of clock, which can be configured on whatever you want. But depending on different ARM cores, depending on different MCUs, you can have different registers. So the thing here is that what we did was basically we tried to have kind of plugin that would help us to understand that code much easier than just be looking and knowing the addresses from the top of our heads. So the other thing that it's also interesting is that when you have a free RTOS OS, basically you will have critical sections. And this is really important because sometimes you cannot wait, you cannot have an interrupt while you're doing something. If you are braking a car, you cannot have an interrupt to say, well, stop braking and keep on. So the ARM processor has 2 specific instructions which allow you to enable or disable the interrupts, which is a good place to start looking. If you are trying to do the reverse engineering of an application, it's a good place because most probably critical code for your application will be inside a disable-enable block of disable interrupt, enable interrupt block of code. So the other thing that we tried to do was basically list all the functions that enable the interrupts, because that will be the end of our block. So we want to go from bottom to up. So in this case, we just list all functions that has the instruction to enable the interrupts, and then we list all functions that basically call that function. And this helps us to understand that in this case, for instance, we are the function the 1e4 disables the interrupts right at the beginning of its execution, and then it will re-enable them really down the code. So if we wanted to understand exactly what that block of code was doing, the good thing would be to try to understand exactly what was going on between that block. So in here, it's the same function, but you'll see that we are calling there the CDC, which we identified as being one of the function that were inside it has the code to re-enable the interrupts. Now, enable and disable the interrupts is not that linear, because there are a group of each interrupt will have different priorities, and there are a couple of priorities that will actually make the kernel of the RTOS to stop and execute the function the handler that handles that interrupt. So it really depends on the priority of your code. Again, there are registers that are used to define the priorities of each handler. And again, that's just a register inside the MCU. Just need to look at the documentation, and you'll have exactly what register we are talking about. So there are a couple of other really interesting registers, like the sysconfig-ext, which is basically a register that will manipulate, well, going a little back, all MCUs, they have several pins, and those pins will be connected to a multiplier, which basically will be enabled or disabled according with the bits that you have. So what this means is that you basically have, well, depending on the architecture, but on this architecture you have two buses which have several GPIOs, and then you need to select which ones you want to check. So this register, the sysconfig-ext, which basically allows you to configure which external interrupts you want to have into your MCU. Then you have the EXTI register, which basically allows you to define the handlers for those interrupts and the pins that you'll have. Also, the clock source we have already talked about. The NVI register as well, the nested vector interrupt control, which also it's the one that allows you to define the interrupts that you will have. So how you handle those interrupts and which are the priorities that you have on those interrupts. If the EXTI allows you to define which ones are the external interrupts that you will be using and on which pins, the NVI will allow you to define the priority of those interrupts. And then we have the clock, which is also interesting because if you want to have a GPIO external with external data to read from a flash memory or from some other kind of external device, you'll need to give it a clock. So even if you don't find the address that allows you to identify which pin you are using, you can check this register to see which pins are being enabled, which GPIOs are being enabled. So it gives you a clue or where to find afterwards what you need. So and based on this, basically what we did was, well, we defined the list of registers. So the plugin that we did when it's executed basically will search the code for all of these registers, and it will give us this output which allows us to understand which functions are doing what, and at the same time it will also add some code, some comments on the code, so that when you are going through either and looking at the code, you can more or less have an understanding of what's going on. So this is there is a lot of work to be done on this basically because this is highly depending on the MCUs. So not all of them will have the same registers. So we need to implement some heuristics to find registers which are being created dynamically, so that we can also try to help and identify which interrupts and which external devices are being used. There's also another thing that we want to do, which basically looks at the table that we talked about and decodes it automatically, the code that are being pointed to it. well, there's a lot of work to be done, especially because there's so many different MCUs, so many different cores that can be used, that doing this through all of them, it's really, well, it's a huge task of reading documentation and copying documentation. So the idea is that this plugin can be updated by anyone, and then anyone can just basically load it as they need. Another thing that we would like to achieve is the identification of the type of image, which is something that is not that easy. And again, it's highly dependent on the MCUs, on the CPUs. And well, thank you. That's basically it.
So we have time for questions. If you have.
I have one question, but it's because I haven't understood. You were speaking about the interrupt level. Can you re-explain that?
Sorry?
You were speaking about the interrupt level. It's the topic that I have not understood.
So when we enable or disable interrupts, that's possible. The MCU will do that. However, you need to give it a priority. And there are a certain level of priority between 3 and 1, which even though you disable the interrupts, the core will always execute the handler. And even the RTOS kernel will stop to execute that task. So you can really, when we say that we are disabling or enable interrupts, we must be careful, because we cannot assume that will happen 100% of our code. If you have a task which is at 1, even if you are running something else, that handler will be executed when the interrupt occurs, even if you disable them.
It's like the hierarchical, more or less.
Yeah.
Okay.
Yeah.
Thanks.
Nobody? No. Okay.
Okay.
So thank you, guys.
Thank you.